So what do I mean by mechanics? Well, mechanics is just the study of how bodies, and bodies are just anything around us, either move or don't move when they're subjected to forces. And we'll give formal definitions to that a little bit later on, but hopefully you have an idea of what a force means. That's just something that tends to change the inertia of an object, or tends to speed it up or slow it down. So when you think about the different fields of studies of mechanics, you can really segment that according to how the bodies actually move or kind of act when forces are subjected on them. So think about some rigid body around you, like maybe if you're watching this at a desk like I am. By and large, I'm guessing if you push down very firmly on your desk, the shape of the desk will largely remain unchanged. And when a body is subjected to forces and it doesn't actually change its shape at all, we call that a rigid body. So the field of study of those type of objects is referred to as rigid body mechanics. Now, what's happening is, even though we can't see it, there are some very, very slight deformations. But what we're doing from an engineering perspective is we're saying if we can ignore those deformations for all practical purposes, for the analysis that we want to do, we'll just model it as a rigid body and we'll do rigid body mechanics. However, if the deformations are more pronounced, like say, for example, I have something plastic like this and I squeeze it and it physically changes its shape, the study of that type of mechanics is referred to as deformable body mechanics, because that's actually a deformation in the shape of the body. The last kind of subset of mechanics is fluid mechanics, and those are just going to be forces that are subjected to materials such that when they undergo a shear stress, they actually deform completely. So things like actual fluids that you might be familiar with, liquids, these sorts of things, but also gases. So fluid mechanics is very important for those of you that want to study kind of aerospace engineering as well. So when you think about just rigid body mechanics, which is what you're going to start with, and everyone's going to start with it, whether you're a mechanical engineer or a civil engineer, obviously you're definitely going to start with it. But even within electrical and computer engineering and the other fields of engineering, you typically take at least a statics and dynamics class. Oftentimes they're combined now into 15 weeks, but you're going to have some basic exposure to this. Now, what do I mean by statics and dynamics? Well, if you have a body that's not accelerating, and we're going to formally define what that means here in a few slides, but acceleration for now, just think of it as it means that the body is not changing its speed. So if it's not speeding up or slowing down, or alternatively, if it's just sitting there, that analysis of rigid bodies that are just sitting there or not speeding up or slowing down is called statics. If a body is actually accelerating, meaning that it's changing its speed, that analysis is referred to as dynamics. So let's think a little bit about the history of the development of statics and dynamics. So if you think about bodies that by and large are just sitting there, ignore the constant speed analysis that's in statics for now. What kind of instruments do you need to take data in that type of analysis? Well, you don't need much, right? You just need basic capabilities to measure lengths and various, very simple things, right? So not surprisingly that since engineering is a very quantitative or data-oriented field, that subset of mechanics developed a lot sooner than dynamics. So the study of statics is very, very old. It actually dates back about 2,500 years. I think I have it noted here, Archimedes' lever. One of the key concepts that we will talk about in static analysis is that in order for a body to remain stationary, not only do all of the forces acting upon it have to add to zero, but also all of the torques, all of the things that are tending to cause rotation have to add to zero as well. And in order to be able to kind of understand that principle of a moment or a torque, a lever is a very helpful instrument. So not surprisingly that a lot of those developments kind of coincide with the development of a lever back 2,500 years ago. When you talk about dynamics, in order to measure how something is speeding up or slowing down precisely, you're going to need a capability to measure time. So probably not surprising to you that the development of dynamics happened a lot later than the development of statics. And if you think about some of the key players in the development of dynamics, you might think about Galileo or Newton. And even though it seems like a long time ago, right, historically speaking, that's really not that long ago. So in order to talk about mechanics, we have to really have a definition of the basic physical quantities of the field. And when you're doing mechanical analysis, there are four basic physical quantities that you want to keep in mind. The first is obviously length. So when you're going to be describing bodies, you need to describe their size, or you need to describe their distance in between them. You're going to need a measure of length in order to do that. In addition, as we mentioned previously, if you're going to talk about how something is speeding up or slowing down, you're going to need a capability to measure time. In addition, we'll see that Newton's laws, when we get to that in the next set of slides, what the fundamental relationship between the forces acting upon a body and how it's actually changing its speed is related to mass. Mass is just a measure of how much actual matter is with an object. And oftentimes it's called the inertia to forces, because the more mass that you have, the less likely you are to move under a set of forces that you're subjected to. And force is just the fundamental quantity that just allows objects to interact with one another. And there's two types of forces that you want to be aware of. There's the force that everyone kind of knows. If you actually push on an object, you exert a force on it. However, you can have forces that act at a distance, particularly the one we're probably all familiar with is gravity. The reason that we tend to fall towards the earth is an attraction to the actual center of the earth there, right? So be aware of that. And in addition, note that there are other kind of action at a distance forces largely associated with electromagnetic quantities. Note that when you talk about forces, they're a little bit different than those three quantities beforehand. They're vector quantities, right? And in order to describe a vector, you need a magnitude and a direction. But in addition, when you describe the effect of a force, it's also very important to describe the point at which it's being applied. Because I can apply the same force to a body, and if I apply it at different points, it will induce different types of motion. You can see that naturally. If I push a certain amount on the body in its middle versus the top, when I push at the top, it's going to tend to tip it more. It's going to tend to induce a larger amount of rotation there, because it turns out that the physical moment, and the moment is nothing more than a fancy word for torque, is dependent upon the actual point of application of a force. So when you talk about static analysis, which is going to be the first thing that we're going to be doing, remember that even though the underlying math is going to be really simple, it's kind of related to fundamentally what we always try to do as engineers. So as engineers, you're not paid for kind of sophistication in your analysis. You're paid to get the job done. So you always want to do things as simple as possible initially. So what we're trying to do is any factors that are in a scenario that don't relate to or won't change the underlying analysis that we're doing, we want to get them out of our model when we're actually doing the analysis. So one of the first things we're going to look at is what's known as particle-based analysis. And I'm sure when you hear the word particle, you think naturally of bodies that are really small. But just know, I want to put it in your head now, because we're going to talk about it a lot more next week, that when you analyze a body as a particle, it doesn't mean that it's small. It just means that we can get the quantities of interest that we want for that particular body under those particular loading conditions, just ignoring its physical dimensions. So the physical dimensions exist, and we're certainly going to consider the mass of the object, but we're just going to ignore the physical dimensions for now, because we can do the analysis for that particular case without it, and we want to get things done as simple as possible. So in addition, the analysis that we're going to do is always going to be rigid body-based analysis. We're not going to consider the actual deformations. And note again, just to repeat it, that rigid body analysis means that when forces are subjected on a body, that they don't meaningfully change their shape. One final point that I want to make is that a concentrated force just takes something that is naturally a force that's distributed over a body and models it as a single force acting at a single point. So think if you were outside on a windy day and there's a bunch of wind blowing on a stop sign. The force that that stop sign is subjected to is really distributed across its entire area. However, we could come up with an equivalent model where we take the effect of that force that's distributed over the entire area in the form of a pressure, and we replace it by a single force. That single force is not actually what's going on, but we're going to use it because it will allow us to kind of have the simplest solution to what we're trying to do. So let's think a little bit more detail about what we just discussed. So let's look at this figure here to the right, and I'll read the text to you. We have a white arrow that's being drawn to show the contact force between the actual wheel and the rail. And I asked you two questions. I said, why are forces drawn as arrows? Well, hopefully everyone knows that from the content that we discussed in the past week with vectors. Naturally, when you draw an arrow, you make two choices. You decide how long to make it, and you decide how to orient it. And so vectors are very well represented by arrows, as we've spoken of. Remember that the one additional thing that makes a force unique is you have to describe the point of application, and we can do that by simply aligning, hopefully everyone remembers, with vectors, this is tail, this is tip. We can place the tip at the point of application. Second question, assuming the wheel is made of steel, why would rigid body analysis assumptions likely be valid? Well, naturally, if you think about all the forces acting on that wheel, if you've ever seen a railroad wheel, it's not very likely that it will deform under normal loading conditions given that type of material. So if there are no changes in the actual physical dimensions of the body, then rigid body analysis is going to be good enough because it will keep our analysis as simple as possible. So hopefully that was a lot of refresher, but hopefully some of you are at least interested in doing basic static analysis. One of the hard things about teaching an intro to engineering course is everyone's interest varies. So we're just trying to keep things, give everyone as broad of a kind of introduction to topics that you'll need throughout the remainder of your coursework as possible.